In this section, we want to investigate different notions of convergence for sequences of functions. Actually, only two different ones, but anyway. So we have seen sequences of functions in the end of the last section, but let's start off a bit more naively. We will introduce later on the notion of uniform convergence of sequences of functions. This is actually the same as convergence in the soup norm as we investigated in the previous section, but let us start from the beginning. Assume we have a sequence of maps. So very general maps between and yeah, what's kind of the most general notion or the most elementary notion that we can say that this sequence of functions converges against something. And if you think about it, the most basic notion would be this one, and this is kind of the most elementary and most general thing I can say about convergence of sequences of maps. So definition 1118. So let X be a set and Y be a metric space. Let Fn for each n be a map from X to Y, where n in n, and assume we have another map F also going from X to Y. So what's the most elementary notion of convergence? This is what we will call pointwise convergence. The sequence Fn, this is now a sequence in the set of maps from X to Y. This is, in that sense, we can consider it as a sequence. This sequence converges pointwise to F, to F, if the following holds. If pointwise means if we fix a point in X, then we want the values of the sequence to converge. So the limit as n goes to infinity of Fn of X at each point X, this is now a sequence in Y. This should be the same as F of X, and this should hold for all X in X. This is why we have the name pointwise. We just choose some X, some fixed point there in X, and then study this convergence separately or individually for each X in X. Now, here this is kind of the most general setting in that sense that we can say X can be an arbitrary set and Y can be an arbitrary metric space. So here we use the notion of convergence in Y in the metric space Y. We will later on mostly use Y equal to R or to C, so we will only consider a basic case in this section, but anyway, this is the most general notion of convergence of sequences of maps. Now, you can ask a very naive question, and this is of course not very precise. Is this a good notion of convergence? And good, let me put here in quotation marks, so it's of course in the eye of the beholder, but is this a good notion of convergence? Okay, what do I mean by this? The idea is now, if I have a sequence of functions which has particularly interesting properties. I mean, of course, I often want to, or I use sequences or convergence of functions in general, like we did, for example, when we studied Taylor polynomials or something, to approximate some very complicated function by much simpler ones. We had used polynomials. I mean, I haven't talked about convergence when we talked about Taylor series before, or Taylor polynomials, but we approached complicated functions by polynomials, and we had a better and better approach in certain situations, a better and better approximation. So this could be seen as some idea of why we should study such sequences of functions. So we want to approximate complicated functions by simple ones. Now, the question would be, if these simple functions have a particularly interesting property, for example, if they are all integrable, Riemann integrable, or if they are differentiable, or if they are continuous, does the limit get the same properties, or can we kind of translate the same property? And for example, if the sequence, if this would be a sequence of differentiable functions, which would converge against some other function, would then the sequence of derivatives also converge against the derivative of the limit function? So is kind of taking a limit then compatible with taking derivatives, or then the same way with taking integrals? So the problem is, the answer here is no. And so let me formulate this a bit more precise. So assume that I be some interval and Fn from I to R be a sequence for all n in n, and assume we have another function which should serve as our limit, from I to R such that the sequence converges pointwise against F. So Fn, n and n converges pointwise to F. So the question would be, if Fn is continuous, let's get numbers to them. This would be little I is continuous for all n and n. Is F continuous? So second question, if I is a closed and bounded interval, so I is equal to AB, and Fn is a Riemann integrable, is F Riemann integrable? And is the following true? Is the limit of the integrals, so limit of n to infinity integral AB Fn of x dx, does this then converge? I mean, this is a number, so now a sequence of numbers. Does this converge to the value of the integral of f? And thirdly, differentiability. If f is differentiable, if Fn is differentiable for all n in n, here also, of course, for all n in n, sorry about that. So if Fn is differentiable for all n in n, is f differentiable? And is then the limit of n goes to infinity Fn prime also f prime? So so this is not very precise because I haven't defined this yet. This is also meant pointwise. So does then the sequence of derivatives converge pointwise against the derivative of the limit? We don't know at this point. So okay, no question mark here. So does this hold true? Here, sorry, I forgot one thing. So this is pointwise convergence, and then f is called pointwise limit of the sequence of Fn. Sorry. Okay, back to the question. So these are kind of inheritance properties. So does the limit inherit some properties from this sequence? And so as I already mentioned, the answer to all of the three questions is no. Answer to 1, 2, and 3, no, not in general. Why is that? I will show you for each of the three cases, I will give you a counterexample. So in the first case, so if we have a sequence of continuous functions, is the limit again continuous? And there's a very simple example, namely take Fn defined on the interval, closed and bounded interval from 0 to 1 to R. F of x is x to the n. Okay, what if, let's maybe draw the graph here. So if this is 1, we have 1 here. Okay, then we know we get some color in there. So for all elements of the sequence, we always know that, Fn of x. Fn of 0 is always 0. So everything starts at 0. And Fn of 1 is always 1. So we always meet here in this point. And you of course know, like for n equal to 1, we just get the diagonal line here. For n equals 2, we would have some segment of parabola, so to say. And this would, for higher indices, this would look similarly, but with a slight difference. So this is taking longer to rise up, and then it's going steeper up there. So we would get like this, and at some point we would have a function which is like this, and so it's getting further and further to the steep thing. So yeah, and so on and so on. Now, what does this converge to? We see that if we take the limit of fn of x, we have to distinguish between two cases. So first of all, here for 1, everything is just 1. So the sequence is constant there, meaning that it's 1 if x is equal to 1, but if x is smaller than 1, then we've seen that if we increase the exponent and increase, this goes to 0. So this is 0 if x lies between 0 and 1 with 1 excluded. So this is what we get there. But if we take the function, this function there, this limit function, I mean, what would that be? If we just denote this here, this would mean we would have, this would be constant equal to 0 here, and here would have a point there, and here would be a gap, and obviously this is definitely not continuous because there is a jump in 1. So, but f of x, which is 0 or 1, so 0 for x in 0 to 1, and 1 if x is equal to 1, is not continuous. So we have a sequence of continuous functions. We know that the powers here, the power functions are all continuous, and the limit is not continuous, although it's a pointwise limit. So there we see, in general, the answer to question 1 is no. There's a counterexample. Okay. Now, what about 2? So we have Riemann integrability. If we have a sequence of Riemann integrable functions, do we have that this compatibility holds? There I will give you an example, and I will not write down the equation for the function because it's a bit tedious, but I will just draw you the graph of the function I want to use. Then it should be clear for everyone. So let's take, again, the unit interval 0 to 1, and with the following graph. So let's take, oops, again, 0, here's 1. So we will now define the function, yeah, actually I should make this a bit bigger. Okay, here's 1. And so we want it to be in such a way that it first goes linearly upstairs, and then with the same slope in the other, but with the other sign, it gets back down linearly. So this would be a piecewise defined function actually. And from there on, it should stay 0. And now I have to draw, of course, where I put these marks here. This should be 1 over n. And so this must be in the middle here. So this is 1 over 2n. And I want this top here, this peak, to be at height n. So for n for n becoming bigger and bigger, I mean, that's, yeah, this. So here it's completely 0. So what does this mean? What happens if n gets bigger and bigger? So assume we have now some bigger value than in this one. So this, of course, 1 over n, we would get closer to 0. So we would be maybe at this point here. This would be, I don't know, 1 over m. So let's say here m is bigger than n in this picture. So this would go closer to 0. Also then this middle point then would also go closer to 0. This would be 1 over 2m. And this peak would now also be higher if m is somewhere here. That's somewhere like this. Okay. Already messing up the drawing, sorry about that. So here we would have at some point height m. So we would get something like this. Okay. Whoops. Okay, that's not really. Anyway, I hope you can recognize. So what we get is this kind of, yeah, this triangle which gets, so this what's it called? Equilateral? Yeah, gleichschenklich would be the German word. Anyway, this, I think, equilateral triangle, which is kind of getting, yeah, smaller and narrower, but higher and higher. So what would this, yeah, what's about these properties? So this is a piecewise continuous, and you can easily see that Fn is Riemann integrable for all n in n with integral from 0 to 1 Fn of x dx, and now I'm doing this just heuristically and not proving this. So this is the surface area under the graph here. So this means we have we have an equilateral triangle, and so if I take the two halves of the triangle here and put them together, I get a rectangle, and this rectangle has size had length of the size 1 over 2n, and here we have n. So we would get the integral here would be n times 1 over 2n, which is 1 over 2. So the integral of each, all these triangles have the same surface area, it's always area 1/2. Okay, so much about that. So this is what we see. So we also see kind of that the sequence of integrals is constant. Now, what about convergence? Since if we take a look what happens, let's assume we have some fixed point x at which we want to consider the limit of the values of fn at this point. So we see that kind of this is getting narrower and narrower. So if we stand at some fixed x, if the index gets bigger and bigger and bigger, we will at some point pass the point where the triangle ends. So we will be on the right-hand side of the triangle, necessarily. So since for x between 0 and 1, I have to exclude 0 at this point, but since for it holds that fn of x is 0 if n is big enough, and big enough means 1 over n has to be smaller than x, which is the same as fn x is 0 for all n bigger than 1 over x. So at some point, since we consider a fixed point x, we have to we achieve this, so this sequence will always be eventually constant equal to 0. So this holds for all sufficiently big n and n. So the limit as n goes to infinity of fn of x is 0 for all n in n. For all x in 0 to 1. I have now here excluded the point 0, but the function is always 0 in 0, so there the same holds as well. But this is the limit, but the integral of 0 dx from 0 to 1 is, of course, 0, and this is not 1/2, which would be the limit of the integrals. So here in this case the limit is integrable, but the integrals do not behave well with respect to limits. So the limit of the integrals is not the same as the integral of the limit. This is of course really inconvenient for computations. So we would like some better convergence notion which can do this. Okay, all you have to erase, and then I will show you what happens with differentiability. So even there pointwise convergence goes wrong, and we will see why in a second. As a counterexample to the differentiability of the limit, we study the following sequence. We let fn be defined on 0 to 2 pi going to r, namely fn of x is supposed to be the sine of nx over the square root of n. Okay, let's draw a graph again. Whoops. So we have 2 pi. So if n is equal to 1, we just get the sine of x. So this is what we know already. The sign looks as follows. Here we have this behavior, and from there it becomes periodically, but we only care about this interval, so it's this sine wave that we study. So yeah, here the peak is at 1, and so the maximum at 1, the minimum at -1. So what happens if we increase n? Now, sorry, I just said something wrong. So what happens here now? First of all, we rescale the function by this factor 1 over the square root of n. Since n is bigger than 1, bigger than or equal to 1, this means we are getting smaller if n is becoming bigger. Now, here's another n, and this means basically just we're oscillating faster. So this just means we're squeezing the function into this. So a function with some smaller n might look like this, and hope it's not too small for the camera. Let's take a different color. So we wouldn't oscillate as much as there, but we would oscillate faster. Wow. Yeah, not really, but you get the idea. Sorry. Some smaller waves, and that get faster in there. So what happens there if n goes to infinity? So what about pointwise convergence? So then it holds that the limit of n to infinity fn of x, this would be the limit sine of nx divided by the square root of n. So the question would now be, also if I had an audience, I would ask what happens in the limit. And this is really only mathematics 1. We see the numerator here. This is a sequence. I mean, x is considered as a fixed number in there. This is bounded. And this is multiplied with 1 over the square root of n, which is going to 0. And we saw that if we have a bounded sequence multiplied with a sequence converging to 0, the limit will again will be 0 for all x in 0 to 2 pi. So we see also, because the sine function is differentiable, so fn is differentiable for all n in n. So if it would behave as we wanted, the derivatives of the function would also have to go to 0, because 0 is a derivative of 0. So let's check and see that it doesn't. So the derivatives fn prime of x, this is very easy. This is just by the chain rule. We have the cosine of nx multiplied by n, the interior derivative here, divided by the square root of n, and this is just square root of n times cosine nx. Okay, and now depending on the sign, I mean, if you take a look at what happens here, this is definitely divergent, because this tends to infinity. This is just behaving quite wildly. So this is not, so fn of x, fn prime of x, n in n diverges for all x in 0 to 2 pi. Yes, no, it's correct, yeah. Okay, yeah, so much for that. So this diverges, so it's again a counterexample to our preferred behavior that we would like to have. So to put a long story short, we want to have a better notion of convergence. This pointwise convergence is simple, but it's not good. It's not really useful. And so I will introduce this notion of uniform convergence. And the good news is this uniform convergence is precisely what we did in the last section when we studied the soup norm. Let x be a set. And for simplicity, I'm only studying the case of bounded functions. Sequence in the space of bounded functions from x to k. Just keep this in mind. Of what I'm doing now, there are generalizations of this for unbounded functions and so on. But I'm only considering the simple case, and also you could generalize many things to not taking values in k, but in an arbitrary metric space. But I want to keep things simple. So let's just consider this case here at this moment, and I will even further restrict to a simpler case later on. So I'm basically doing this because this is, for now, this is sufficient for you, so you really don't need that much more. Okay, so this is a sequence in bxk, so, and we take another function f, which is also a bounded function from x to k. Okay, we say that fn n in n converges uniformly to f if it converges in the soup norm, meaning the limit of n to infinity of the norm of fn minus f infinity is 0. By a remark that I made in section 11.1, this is sufficient. This would be the distance of fn and f, which goes to 0, which means it converges in the metric space, to be precise. But this is the crucial thing. So if this limit here is 0. Okay, so this is what we've already seen, and we've seen that b of xk is complete. So this is, this makes sense in some sort of Cauchy sequences converge, which is also a nice thing there to have. So we know that some limits exists in this notion of convergence, which might otherwise not if we have a Cauchy sequence. Now, in this case, then just some additional notation. We then write f is the limit of fn. So just without any point or something, we just write f is then the limit here, and call f the uniform limit, or if it's clear that we are always studying uniform convergence, just the limit of Fn. Okay, so much about that. Sorry, little mistake. Let's see an example and a counterexample. So example 1120. Let's consider the following sequence of functions. Fn from 0, 1 to r. Fn of x is x squared plus 1 times e to the x divided by n. So, this sequence of functions here. We want to show that this converges uniformly. Now, the first thing is, of course, if you want to show uniform convergence, you need a candidate for a limit. You need to get what f is. And for this purpose, let's check if it converges pointwise or what it converges to pointwise, and then try to show it converges uniformly. So, compute its pointwise limit. So the limit n to infinity fn of x for some fixed x. This is the limit as n goes to infinity of x squared plus 1 times e to the x over n. And of course, this is just constant in terms of n. So this is x squared plus 1 times the limit as n goes to infinity of e to the x over n. And there we see here the exponent goes to 0, and by the continuity of the exponential function, this means, so by continuity of exp, this yields that the limit n to infinity of fn of x is x squared plus 1 times e to 0, because the exponent sequence converges to 0 for all x. And e to the 0 is 1, so we just get x squared plus 1. So this holds for each, for all x in 0, 1. Okay, so this should be our candidate for the limits. So that f from 0, 1 to r, f of x be x squared plus 1. And now we want to show that the sequence really converges uniformly against this. So I want to show Fn n in n converges uniformly to f. Okay, how do we do that? Now we do a nice estimate for all x in 0, 1, we compute the following. So the sup norm is defined by taking the suprema of the expressions fn of x minus f of x in that case. So the suprema of these expressions that need to become smaller and smaller, so go to 0. So let's check. Let's insert the definitions. This is x squared plus 1 times x e to the xn minus x squared plus 1. And if we just reorder the terms, this is the same as the absolute value of x squared plus 1 times the absolute value of e to the xn minus 1. Okay, so this is obviously a positive number, and x squared, as x is between 0 and 1, this expression here can become at most 2. So let's estimate this by saying this is smaller than or equal to 2 e to the x over n minus 1. Okay, and for this expression, we just make this very simple observation. Since exp is, now the real exponential function, so e to the x is monotonically increasing, we can make the following observation. Sorry, another mistake. e to the x over n. X is between 0 and 1, so this is smaller, bigger than or equal to e to the 0 over n, so e to the 0, which is 1. Now, x is smaller than 1, so this is smaller than or equal to e over 1, e to the exponent 1 over n. So, first of all, from this first inequality, we see that we can ignore the absolute values because this is always non-negative. And here we can see that we can estimate it then from above, namely it follows that, so fn of x minus f of x to the absolute value is smaller than or equal to 2, and now without the absolute values, e to the 1 over n minus 1. And also, yeah, first it's now made 2 step in 1. So the first inequality shows that we can remove the vertical bars, so the absolute values. And now we can use this estimate here to show that this is smaller than 2 e to the 1 over n minus 1. Okay, so this holds for arbitrary x. So this means the sup norm fn minus f to the infinity, which is the supremum over all these expressions, since this shows now this is an upper bound for these expressions over all x. Since the supremum is the smallest upper bound, we get that this is smaller than or equal to 2 e to the n, e to the 1 over n minus 1 for all n in n. So we see now this is an upper bound, but we see that if n goes to infinity here, this expression here goes to 1, so the term on the right side of the inequality goes to 0. So we know that, yeah, since the limit of, as n goes to infinity, of 2 e to the 1 over n minus 1 is 0, and we know here on the other side that the norm is always non-negative, so this is 0 smaller than this. This is time for the squeeze lemma, the lemma for functions. So this is or squeeze theorem, I call it. Squeeze theorem yields that the sequence is in between two sequences going to 0, so the limit as n goes to infinity fn minus f to the sup norm is also 0, and this is of course by definition means that the sequence goes uniformly to f, so the limit of fn is f. Okay, so counterexample. We have already seen counterexamples, namely the counterexamples to questions 1 and 2. Do not converge uniformly. And I will not prove this here, but I encourage you very much to write down why. Take the functions I had before and take a look at the supremum norms here, and then you will easily see why this cannot go to 0. Okay, these are the so far counterexamples. Now let's move on. First of all, I want to give a statement where you can characterize the uniform convergence in a more explicit way. And let's take a look at this. And this already gives an indication because I will now write down a more explicit form of the convergence in terms of epsilons and so on. And this also gives a nice idea about how to compare pointwise and uniform convergence and to really spot the difference there. So X is a set. Fn is a sequence in Bxk. Oh, I think I forgot to mention in the beginning. I'm really sorry about that. K is just R or C. Sorry. It's probably what you thought about. So K is equal to R or K is equal to C. In both cases it works. Sorry about that. Whenever I'm writing K today, it's always R or C. Okay. Let this be a set. That this be a sequence in Bxk. Then, oh yeah, and a limit function here, f in Bxk. Then the following statements are equivalent. Let me again abbreviate. The following statements are equivalent. 1, the sequence converges uniformly to F. 2, for each epsilon bigger than 0, there exists an n0 in n such that fn of x minus f of x to the absolute value is smaller than epsilon for all n bigger than or equal to n0 and for all x in x. This is the crucial part here, and I will explain more about this and give you an idea of how to prove this after I erased.